Okay, let's start with question number 6. We have a synthetic organic antibacterial compound used in the urinary tract infection. Serum concentration were reported following IV bolus administration of oops, this is too much. I think because it's too focused. Anyway, yes. Okay, dose of 250 milligram to 9 healthy male volunteers as table here. Okay, notice that we have time in hours and we have the concentration in microgram per milliliter plus or minus standard deviation, and this is what we have here per number. This is the concentration and this is standard deviation because we are talking about 9 healthy volunteers, not one subject. And usually that's what you find when you do studies. You're not talking about one subject only. We are talking about a group of subjects, so we need to do some statistics. Okay, but for our for the sake of our dose, we will take only the concentration as it is. Okay, and then we will use those information to determine what is needed here. We need to determine half-life, we need to determine K, apparent volume distribution, clearance, total clearance, and area under the curve, serum concentration. Then we'll go back to this. Okay, first of all, we have concentration in microgram per milliliter versus time. And again, you need to draw it or profile it using the right way or right axis. So in here we have it log concentration versus time in hour, and this is our linear regression equation, okay, of log CB versus time. Okay, so let's write it here and start working on it. Minus x plus 10613. Okay, you can, by the way, try in all of the questions that we did if the question was in a length term and the same equation. So use this equation for your practice. If it was on length terms, what would be the difference? Okay, but this is in log terms, so it's actually serum plasma, but I will call it versus time. Okay, so it's linear regression of a log CB versus time. This is your slope and this is your y-intercept. Okay, and as I mentioned before, you can use this slope, which is equal to minus k over 2.303, to determine k, which is 0.609 or minus 1. Okay, and we can use this to determine the half-life over 0.609, which is equal to 1.137 hours. Okay, and we can use this to take the antilog of it to determine concentration, initial concentration, and this is equal to 11.516 microgram per milliliter. Okay, I can use this to determine VD because I know CB node equals X node over VD. I need to know this. I have this as 250 milligram, and I have this, which I already determined. Then VD is equal to 21.71 liter. Okay, then it's asking us about total clearance. Total clearance would be equal to K multiplied with VD, this 609 or minus 1 multiplied to 2.17.1 liter. Okay, this give us 13.22 liter per hour. Okay, another variable that is asking here is area under the curve. and it's total area under the curve. Okay, area under the curve, and again, total area under the curve equals, if you remember, it's x naught over k multiplied with VD, which is what? Total clearance. So it's equal dose over total clearance equals area under the curve. Do we have those? Yes, this is 250 milligram. Okay, and this is the one that we just determined, liter per hour. Okay, so area under the curve, which is total from 0 to infinity, equals 18.9. If you go to the unit of this, would be milligram over liter per hour, or milligram hour per liter. Okay? Let's go back to the question and read the last part of it. The urine samples were also assayed for unchanged drug and metabolite. Okay, so we have unchanged drug and a metabolite until 24 hours. The percentage of the administered dose recovered in the urine as unchanged drug was 50.1. Determine renal clearance, metabolic clearance, excretion rate constant, and metabolic rate constant. Okay, let's go. So notice that we have a number here, which is, I want just to have all the numbers that we need. So we have a number in the question that it's 50.1 percentage. Okay, what is that? You need to ask yourself what is that and make sure that you have it right, because everything after that, it will depend on the percentage that we have here in the question. Let's reread what the question gives us. The percentage of the administered dose recovered in the urine as unchanged. So this would be the fraction of the drug excreted, right, in the urine, because it's unchanged. Okay, so we can determine the fraction of the drug metabolized, which will be equal to 100, which is total, minus 50.1, which will be equal to 49.9%. Okay, so sorry, this is percentage. I'm so sorry. Okay, so this is the percentage of the drug excreted versus the drug metabolized. Can we determine the fraction? Yes, which would be equal to 50.1 over 100, which will be equal to 0.501, the percentage of the drug metabolized, which will be equal to 49.9 over 100, and this will be equal. Okay, both of them should be equal to 1 for sure, because we are talking about the fractions and 2 part of the total, which is 1. Okay, so it's asking us about renal clearance, metabolic clearance, KE and KM. First order excretion rate constant, first order metabolism rate constant. Okay, you can either start with K's and go back to clearances, or start with the clearances and then go back to K's. Okay, you can do whatever you want. So let's start with the renal clearance. Okay, renal clearance would be equal to the K excretion multiplied to VD, right? Or would be equal, the fraction of excretion would be equal renal clearance over total clearance, right? And the same thing for the metabolic. You can use any one of them. So the metabolic clearance equals Km, use the right constant, multiplied to VD, or the fraction of metabolism equals metabolic clearance over the total clearance. Okay, so let's use oops. Let's use the part related to the percentage of the total. Okay, so we need to determine or to know the total clearance. If you didn't calculate it, or it's the question didn't ask for it, you need to calculate it. So if the total clearance equals 13.22 liter per hour, then renal clearance, which is here, right, equals fraction excretion multiplied to the total fraction excreted as, right, 0.501 multiplied to 13.22, then the answer is 6.6 liter per hour. This is the renal clearance, okay? Can we determine the metabolic clearance? Yes. You either say the metabolic clearance equals total clearance minus renal clearance, okay, which will be equal to 13.22 minus 6.62, or you also say that it's equal fraction of metabolism multiplied to the total clearance, which will be equal to the fraction of the metabolism, 0.499 multiplied to 13.22, which would be equal to 6.60 liter per hour. This is the metabolic clearance. And we can notice that they are very near to each other because the percentage is very near to each other. After that, we can use this for each one of them to determine the case or the constants, okay? If the renal clearance equals KE multiplied to VD, okay? Do we have the volume distribution? Yes, we do, which is equal to 21.71, okay? Okay. So we have this, and we have this, and we need this. So KE equals renal clearance over VD, which will be equal to 6.62 over 21.71. So, sorry, this KE be equal to 0.305 or minus 1. Okay? For determination of Km, we can do the same thing, which is Km multiplied to Vd. I have this, I have this, I need this. Or you can just say that it's total K equals Km plus Ke, and we have this, and we need this, okay? You can use any of them, okay? So let's do this. Metabolism, Km metabolism multiplied to Vd. Again, we need this, so Km equals over Vd, and this is equal 6.61 over Vd, which is 21.71, and then Km equals to 0.304 or minus 1. And by this, we finished, I think we finished the question, right? Yes, we finished the question, okay?